So welcome you all to IGC again. So this session will be discussing about the previous year solutions of GATE 2010 question paper of Aerospace Engineering, and we'll be focusing on questions related to aerodynamics. All right. Okay. So let's get started with this. So if you see GATE 2010 question paper, you will find that there were 5 questions of 1 mark from aerodynamics and uh, 4 questions of 2 marks, right? So total marks for aerodynamics was around 13. So I had told you this yesterday also that in typically in any question paper, you can find around 10 to 15 marks questions from aerodynamics. Okay, so it has a considerable weightage, right? So now let's start looking into these questions one by one, and let's see how to solve them, right? So uh, I hope you guys are ready. Shall we start? Okay. Yeah. So this is the first question. If you see in GATE 2010 paper, this was question number 14. So this was again a 1 marker question. Okay. It's an MCQ. So let's see what this question says. Consider an incompressible 2D Couette flow of water between two walls spaced 1 meter apart. Okay, so you have two walls. You can see the figure over here. You have two walls, okay, and they are at a separation of 1 meter. Lower wall is kept stationary. Lower wall is not moving, and the upper wall is moved at a constant velocity of 2 meters per second. Okay, what is asked is what is the shear stress? Okay, shear stress. So basically you need to find tau acting on the lower wall. Okay, so you need to find tau wall. So we generally represent that by tau subscript w if the upper wall is moving at this much speed, right? And you are given the viscosity, absolute viscosity of water, right? So to solve this question, you must go back to your fluid dynamics, right? In your fluid dynamics, you must have studied different flows, right? Flows through pipes, flows through channels, flows through parallel plate, with parallel plate moving. So this is one such question of a moving plate. Okay, you have two parallel plates and there is a flow between them, and one of the plate is moving at a constant velocity, right? So such flows are generally known as Couette flows. Okay, so let's now discuss what is this Couette flow and let's see how to solve this problem, right? So you basically have two plates. Okay, you have two plates. The upper plate is moving with a velocity, say up. So here I'm discussing a very general problem of Couette flow, and then once we arrive at the expression for the shear stress, we'll substitute the values and find the answer. Okay, so let's now understand this Couette flow. Okay, so you have the flow through this through both these parallel plates, and the top plate is moving, right? Now you must understand that in Couette flow there are two different varieties of problems. Okay, two different varieties of problems. The first variety is that is a plain Couette flow. Okay, plain Couette flow, and the second variety is Couette flow. Couette flow with a pressure gradient imposed. Couette flow with a pressure gradient imposed. Okay, so which is this condition, which is the variety of problem that is given in this particular case? You can read the question. They have not told anything about any external imposition of pressure gradient, right? So this problem belongs to a plain Couette flow. Okay, this problem belongs to plain Couette flow. Okay, so it's important to understand that here no pressure gradient, no pressure gradient is imposed. Okay, pressure gradient is not imposed in this condition, right? Now, why is this important to understand this point? Because guys, in Couette flow, the main driver of the flow is the top plate, right? The top plate is moving at some velocity. There is going to be no slip condition at the top and bottom plate. So the velocity is going to be zero because it has to follow no slip condition because the flow is viscous, right? But the top plate is moving. So that top plate is going to move the entire flow domain, right? So the driver of the flow over here is not the pressure gradient, but the motion of the top plate. Okay, so it is important to understand that no pressure gradient is imposed. So for such a case of plain Couette flow where there is no pressure gradient imposed, it is the velocity profile of a fluid element. If you just take a cut section of this plate, you will find that the velocity profile is going to be linear, right? It is going to be linear. So it is going to be the maximum at the top. What is going to be the velocity at the top, guys? What will be the velocity at the top? It is going to be the velocity of the plate, which is equal to UP. And what is the velocity at the bottom? Yeah. What is the velocity at the bottom? Those who are watching the session can comment. What will be the velocity at the bottom? It will be zero, right? Because the flow has to follow the no slip condition, right? So if you see the velocity profile, it's going to be like what? The velocity profile is going to be linear. Okay, it's going to be a linear velocity profile. So only for such a case of a plain Couette flow, you find that velocity profile is linear. So this type of velocity profile, you can guess it from your intuition. Okay. Yeah, right. You are right, Punya and Ashish. Yeah, great. So this type of velocity profile, you can guess it from your intuition, from your understanding of the flow physics, right? But say what I don't even know what is this Couette flow, and say you are not able to guess it, then how will you arrive at the velocity profile? So for that, we have to go back to our Navier-Stokes equation, right? So let's go back to our Navier-Stokes equation and let's write down the Navier-Stokes equation for 2D incompressible flow, right? This is a 2D incompressible flow. Okay, so let's write down our Navier-Stokes equation for 2D incompressible flow. So which is the first equation in the Navier-Stokes equation, guys? Can you say which is the first equation? So which are the which set of equations are generally called as Navier-Stokes equation? You have continuity equation and momentum equation, right? So we start from the continuity equation. So what is the continuity equation? Dou u by dou x plus dou v by dou y is equal to 0. This is the continuity equation, right? Right? This is the continuity equation. Now let's see what happens to this particular case. So in this case, you can see the flow is fully developed, right? The flow is fully developed. So because the flow is fully developed, you will achieve translational independence. What do you mean by translational independence? Flow properties will not vary along x, right? So you fix your coordinate system, say this is x and this is y, okay? And say this separation is some h, okay? So there is going to be no variation along your x. So whatever variation is along your x is going to be 0, okay? Because the flow is fully developed, right? And what is the another assumption? Flow is steady, right? So dou by dou t will also be 0. So your time derivatives, the local time derivatives will also go to 0, okay? What else is there in this problem? You see, what else is there, guys? You also see that there is only variation in x component of velocity, right? There is no variation in y component of velocity. The y component of velocity does not even come into picture, okay? So you see that v is equal to 0. There is no y component of velocity. So if you apply these conditions, to the continuity equation, you will see that the continuity equation vanishes, right? Because dou by dou x is 0, v is 0, So the continuity equation is already satisfied. Now let's apply the x momentum equation. Let's apply the x momentum equation. So what is the x momentum equation, guys? You have u dou u by dou t plus u dou u by dou x plus v dou u by dou y is equal to minus 1 by rho dou p by dou x plus mu times del square u by del x square plus del square u by del y square, right? This is our Navier-Stokes equation or the x momentum equation, right? So now let's see what happens to the x momentum equation. So what will happen? Let's go term by term, right? You see the first term. First term is an unsteady term. We have already told that the flow is steady. So let's strike off this particular term. And you know there is no variation along x, right? So all dou by dou x derivative will go to 0, right? Dou by dou x goes to 0. V is 0, so this term also goes to 0, right? And you know there is no pressure gradient imposed. So dou p by dou x term also goes to 0, right? Now come to this particular term, double derivative terms. See the first term is dou by dou x square, right? Again, you know dou by dou x term goes to 0. So this will also vanish, right? But you see the last term will not vanish, okay? Last term will not vanish. So from this x momentum equation, what do you obtain, guys? You obtain dou square u by dou y square is equal to 0, right? This is the condition you obtain, right? Is it clear, guys? Are you all following? Can you please comment if you guys are following? Up to here, is it clear for you? Okay. I hope it is clear. Right. So we obtain dou square u by dou y square is equal to 0, right? So this is the condition that we obtain. Now what should we do? I want to obtain the velocity profile. So let's integrate this. If I integrate, I will get dou u by dou y is equal to some constant. Let's say that is C1. Again you integrate, you will get u of y is equal to C1y times plus C2, right? You will have two constants because it's a second order PDE, right? So you're going to have two constants. All right. So you got the velocity profile. Now, how will you find C1 and C2, guys? Can someone tell me how will you find C1 and C2? How to find the constants? Yeah, you will find the constants through the boundary conditions, right? So what are the boundary conditions for this case? You know, you have two plates, right? The bottom plate is at rest. Top plate is moving with velocity up, right? So what is the boundary condition in this case? Boundary condition is that u of 0 is equal to 0 and u of h is equal to up, right? This is h. So yeah, Samant, you are right. Okay. So u of h is equal to up. So let's apply these boundary conditions. What will you get? If you apply these boundary conditions, you will see that your velocity profile now becomes up by h times y, right? So now you can very well see, guys, we have obtained the linear velocity profile. So how is the velocity profile for this case? It is a linear velocity profile. Okay, it's a linear velocity profile. So this is what we had from our intuition, and we have obtained that mathematically also from the Navier-Stokes equation. All right. Now, what is that we have to find in this question, guys? What do we have to find? We have to find the shear stress. So how will you find shear stress? Can you tell me which is that equation that relates shear stress to the velocity profile? Yeah. Which equation relates your shear stress to the velocity profile? It is the Newton's law of viscosity, right? So let's apply Newton's law of viscosity. Okay. So what is Newton's law of viscosity? It says that shear stress is equal to viscosity times the strain rate, which is du by dy. So in this case, what will you get? If I want to find shear stress at the wall, then this has to be at y is equal to 0. So tau wall is going to be mu times du by dy at y is equal to 0. So tau wall will be equal to mu times, what is du by dy in this case, guys? It is up by h. Okay. So we have obtained the expression for shear stress at the wall. Okay. Yeah, Ashish, you are right. It is Newton's law of viscosity. So, uh, so now we'll just substitute the values, right? So what are the values? Mu is given to you as 7 into 10 power minus 3. UP is given to you as 2. H is given to you as 1, right? Make sure, guys, you should place the correct units, okay? Don't make any mistakes in units. So tau W is going to be now 14 into 10 power minus 3 Newton per meter square. So you got the shear stress. Okay. So now let's see the options. You have option D, 14 into 10 power minus 3. Okay. So is this clear? See, if you remember the velocity profile of Couette flow already, then you can directly solve this problem. Okay. You don't need to derive it, but I just did it for those who do not remember. Okay. It's not very difficult to derive. It's just few steps, right? All right. Let's now move on to the next question. Okay. So next question, you see that consider an incompressible 2D viscous flow, right? It's a viscous flow over a curved surface. Let the pressure distribution on the surface be P of S is equal to, so expression, right? They have given you an expression in terms of S, where S is the distance along the curved surface from the leading edge. They're asking you to find the point at which flow will separate. Okay. So let's see how to solve this problem. All right. So they have given you a curved surface. Okay. Let's consider you have a curved surface like this. Okay. And they have told you that S is the curvilinear coordinate. Okay. What do you mean by curvilinear coordinate? It means that you are traveling along the surface. Okay. So this is the curvilinear coordinate. So now they have also given you the pressure distribution along this surface. So what is the pressure distribution? 2 plus sine 2 plus sine pi by 2 plus s, right? This is the pressure distribution that is given to you. Let's try to understand when you will have a flow. Okay, when you have a flow, what will happen? How will the flow happen to this curved surface? You see that, so if I draw a hypothetical horizontal line like this, okay, what will happen in this area, guys? In this region, flow is going to accelerate, right? Because you see the effective area is reducing. So by continuity equation, the flow will accelerate. So when the flow will accelerate, your pressure gradient, that is, say dp by dx, pressure gradient is going to be negative. So it's going to be a favorable pressure gradient. Okay, favorable pressure gradient. Okay, and you see that once the flow comes here, okay, the pressure keeps on decreasing. At this point, at a point, you'll see that pressure becomes minimum. Okay, you will find P minimum, and then you see that it is diverging, right? So because it is diverging, your pressure gradient now starts to increase. So this is adverse pressure gradient. Okay, this is adverse pressure gradient. What happens in an adverse pressure gradient, guys? In an adverse pressure gradient, the flow will separate, right? the flow has already separated. Okay, in adverse pressure gradient, you will find that the flow has already separated. Okay, but the separation starts some distance before the adverse pressure gradient, right? So it's basically when the transition from negative pressure gradient to the positive pressure gradient takes place, the flow will separate, right? So from here, we can say that the flow separation happens when your pressure gradient, that is dp by dx, is equal to 0. Okay, when your pressure gradient is equal to 0, that is when you will have your flow separation. What do you mean by flow separation? You are going to have a boundary layer here, okay, and because of the adverse pressure gradient, there will be some flow reversal, right? Flow always goes from higher to lower pressure, so there will be a flow reversal. So you will have the flow turning like this. Okay, that is what is pressure flow separation, right? So that will happen when your pressure gradient is equal to 0. But in this case, we don't have dp by dx, right? In this case, we have p of s, right? So we have to take the derivative of pressure along the curvilinear coordinate. That means you have to take dou p by dou s and equate it to 0. Very simple. Okay, so let's do that. What will you get? So you know p of s. So what is dou p by dou s, guys? Dou p by dou s is equal to cos of pi by 2 plus s, right? Equate it to 0. So when will a cos become equal to 0? When your angle is odd multiple of pi by 2, right? When your angle is an odd multiple of pi by 2. So here, if you see, if you put n is equal to 0, okay, if you put n is equal to 0, you will obtain s is equal to 0, right? But s is equal to 0 is not correct, because s is equal to 0 is a leading edge. So at the leading edge, flow will never separate unless you keep it at very high angle of attack, right? So that is not the case here. So you cannot take n is equal to 0. You should take n is equal to 1. Let's take n is equal to 1. If I take n is equal to 1, what will I get? I will get pi by 2 plus s is equal to 3 pi by 2. From here, guys, can you tell me what is s? What is s? S is equal to pi, right? S is equal to pi. So is it clear to you all? So if you see the options, option D is correct. Okay, option D is correct. Now, guys, also see that in this question, they have given you the pressure distribution over the surface. What if I give you the velocity distribution over the surface and ask you the same question? How will your approach be? Okay, so please think about it. Okay, say instead of pressure distribution, I give you the velocity distribution. Then what will be the condition for flow separation? That can also be one of the possible questions in GATE, right? So please think about it. Okay, all right. So now let's move on to the next question. Okay, this is a very easy question. It's a conceptual question. It is from boundary layer. Okay, so let's see what this question says. This question says, in a 2D steady, fully developed laminar boundary layer. Okay, it's a laminar boundary layer over a flat plate. X is a streamwise coordinate, Y is the wall normal coordinate, U is the streamwise velocity component. Which of the following is true, right? So basically they are asking you in a boundary layer. So when you keep a flat plate, say this is a flat plate, you keep it in a flow, there will be a boundary layer over this flat plate, right? So basically they're asking you what will happen to the gradients, the velocity gradients inside the boundary layer, right? That is what is the question. So you have to compare the gradients, right? So let's, this is a very straightforward question. So it's in fact a statement of Prandtl's postulate. So let's understand what is that Prandtl's postulate. So when you have a flat plate boundary layer, okay, when you have a flat plate boundary layer, so you're going to have a thin layer right? Thin layer close to the surface where viscous effects are more dominant, right? And they have told you it is a fully developed case. It's a fully developed boundary layer, right? So because it's a fully developed boundary layer, the velocity variation along the streamwise direction, okay, along the streamwise direction, you will find that there is no variation in velocity, okay. So the variation of anything along the streamwise direction is negligible, okay. Why? Because the boundary layer is fully developed, okay. Boundary layer is fully developed. So let's understand what is that defines the boundary layer, right? So who has found out that there is boundary layer existing on a flat plate? It was done by Prandtl, right? So Prandtl has given some postulates, okay, that governs the complete set of equations of boundary layer. So there are two postulates given by Prandtl, okay. So let's see what are those postulates very quickly. So postulate one says that fluid viscosity is very small, okay. Fluid viscosity is very small, which means your nu tends to 0. If your viscosity is very small, what will happen to Reynolds number, guys? Reynolds number will tend to infinity, okay. So boundary layer generally happens in a case where your Reynolds number is very, very high, okay, or your fluid can be almost treated to be inviscid, okay. So this was the first postulate given by Prandtl, okay. This postulates actually are at the heart of the boundary layer equations. Now what is the second postulate? Second postulate is that no slip condition, no slip condition has to be maintained, okay. No slip condition has to be maintained. Where it has to be maintained? It has to be maintained at the wall, right? Now because no slip condition has to be maintained, you are going to have a velocity profile. If you see this, you're going to have a velocity profile something like this, okay. So you see that the gradients are actually more along the y direction, okay. So if you draw the coordinate system, you see that the gradients are actually more along the y direction. So it is a consequence of the second postulate that dou by dou y, or say dou u by dou y, is much greater than dou u by dou x, okay. Because your boundary layer thickness delta is much smaller than the characteristic length of the plate, right? So you have a characteristic length, there's a boundary layer, that boundary layer thickness is much smaller, okay. So delta is much less than L. So you can see that option B is a direct statement of Prandtl's postulate. So that is what was asked in this question, okay. I hope this is clear to you all. Let's move on. Okay, this is a very straightforward question, okay. So what this question says, phi is the velocity potential function, okay. It is so this was one of the question of yesterday's session also. We saw that phi is defined for an irrotational flow, okay, and u and v are the velocity components as usual, and you just have to find which is the correct relation between the velocity components and the potential function, okay. So it is fairly simple, right? You know, for an irrotational flow, del cross v is equal to 0, right? The curl of velocity vector is equal to 0. Because of this condition, from the identities of vector calculus, you can always write v is equal to del phi, right? Velocity can be expressed as a gradient of a scalar potential function, okay. You can only write this for a irrotational flow, right? So what does this mean, guys? If you split it into components, you can write u is equal to dou phi by dou x, v is equal to dou phi by dou y. Okay, that's it. So that is what is asked here. You can just match the options. Option D looks the most appropriate one, others are wrong. Okay, see, so in this question the incompressible word is an additional word, it is redundant here, right? It is not required. So even if I strike off this word incompressible, okay, your answer should not change, because remember phi is defined only for an irrotational flow. We have not imposed any incompressibility condition on definition of phi, right? So even if I say the flow is compressible, your answer is not going to change. Okay, so please be mindful of these small things. They can test these things in gate. Okay, all right, so I hope this is clear. It was very straightforward. Let's now move on. So there's the next question. This is also a fairly simple question. Let's do this quickly. So it says an aircraft is cruising at an altitude of 9 kilometer. The free stream static pressure and density. So they have given you P infinity, they have given you rho infinity. Okay, static pressure, static density. A pitot tube mounted on the wing senses a pressure of 3.3 into 10 power 4 Newton per meter square, right? Ignoring compressibility effects, the cruising speed of the aircraft is approximately 1. So you have to find the speed, okay, the airspeed or the speed of the aircraft from the data, from the pressure and density data, right? So when you read this question, it should obviously strike you that the only equation that relates your pressure and density is what? It is the Bernoulli's equation, right? So you have to apply a Bernoulli's equation over here. And they have told you to ignore the compressibility effects. So the flow is going to be incompressible. Okay. So all the assumptions that are applicable for Bernoulli's equation is already present in the question. You just have to apply the Bernoulli's equation, right? Okay. Now, guys, can you tell me what is this Pitot tube? So Pitot tube is going to measure a pressure, right? So when you have a flow, okay, you have a Pitot tube, right? So this is a Pitot tube. So what does this Pitot tube measure, guys? Can you tell me? What does this Pitot tube measure? Pitot tube measures the stagnation pressure, right? It measures the stagnation pressure. So what it measures is basically P naught. Okay. So the flow will come and stagnate at the nose of this Pitot probe, and what it measures is the stagnation pressure P naught. So you are given P naught value, right? What is that? 3.31 into 10 power 4 Newton per meter square. And you are given P infinity and rho infinity. Okay. So that is 0.467 kg per meter cube. And this is 3.08 into 10 power 4. Okay. All right. So this is the data that is given to you. So we just have to apply Bernoulli's equation. So you take 2 points. First point you can take at the infinity condition. Second point you can take at the nose of the Pitot probe. Okay. So if you apply the Bernoulli's equation, what will you get? P infinity plus half rho infinity V infinity square is equal to P2 plus half rho 2 V2 square. Okay. So assume they are at equal height. So the head is negligible. Okay. Now you see at point 2, the flow is going to stagnate, right? So V2 is going to be 0. So the dynamic pressure for the second point is going to be 0. So whatever pressure that is there is going to be the stagnation pressure, which is P naught. Okay. And this is measured by the Pitot probe. So from here, you can say that your V infinity is going to be 2 times P naught minus P by rho infinity square root, right? So you can just substitute your values. Okay. So you can substitute your values and find out the answer. Can you please calculate and let me know what you are getting? You just have to substitute. Okay, this is P infinity. It is a straightforward application of Bernoulli's equation. So what will you get here? You will get around 99 meters per second. But if you look at the options, they have rounded off. So approximately it is around 100 meters per second, right? So option B is the correct answer. Okay. I hope this is clear to you all. Any doubts, guys? If you have any doubts, please feel free to ask in the comment. Okay, let's move on. So the next question is, consider the flow of air with this density over a wing of chord length 0.5 meter, span of 3 meters, right? So chord length is given to you, span is given to you. Let the free stream velocity be 100 meters per second, and the average circulation around the wing is given to you, right? This is the circulation around the wing. They're asking you the lift force acting on the wing. So you know there's only equation that relates your lift to circulation. You know that your lift is going to be directly proportional to the circulation. What is this theorem called, guys? This theorem is called Kutta-Joukowski theorem, right? Kutta-Joukowski theorem. Okay. So you have to apply Kutta-Joukowski theorem here. So what is Kutta-Joukowski theorem? It says that lift per unit span is equal to rho times the free stream speed times the circulation. Okay, rho, u, gamma. Okay, it's the multiplication of all three. So all the values are given to you. You just have to substitute. Okay, so the lift is now going to be, density is given to you as 1.23, velocity is given to you as 100, circulation is 10. See, this is lift per unit span. So if you want to get the lift, you have to multiply by the span of the wing. So what is the span given to you? 3 meters, right? So 3. Okay. So if you multiply, what you're going to get? You're going to get 3690 Newton, which is option C, right? So it was a fairly straightforward question. You just had to apply Kutta-Joukowski theorem. This comes from the circulation theory of lift. If you want to know more about this, please refer John D. Anderson. Okay. It has proper explanation on the circulation theory of lift. All right. Let's now move on to the next question. Okay. So this question is a little bit involved. So I mean, I'm sure you would have come across this already, but let's see how to solve. So it says consider a potential flow over a finite wing. Okay, so this is a question of finite wing aerodynamics, right? With the following circulation distribution. So you can see the figure over here. This is the wing. Okay, this is the wing, and this is the longitudinal axis of the wing, that is y-axis. Okay, and along the wing, span of the wing, they have given you a distribution of circulation, right? So gamma of y is being given to you. If you look at this, what type of circulation is this, guys? This is what type of distribution? This is a elliptical distribution. Okay, it is a elliptical distribution. So they have given you an elliptical distribution of circulation, and you have to find out what is the induced angle of attack. You have to find what is alpha I. Okay, so when you get an elliptical distribution of circulation, you need to follow some steps. Okay, you need to follow some steps to arrive at the induced angle of attack. So how will you find out induced angle of attack? You know, induced angle of attack is given by minus W of y naught by V infinity. Okay, what is W of y naught? This is the downwash. So it is the downwash by velocity that gives you induced angle of attack. So the free stream velocity is already given to you, but you have to find out the downwash, right? So how will you find the downwash? For that, you have to go back to your LLT. Okay, what is LLT? LLT is the lifting line theory. If you look at John D. Anderson lifting line theory, Prandtl's lifting line theory, you will find out that it has proper steps on how to arrive at different geometrical parameters of the wing based on lifting line theory. Okay, so you are given the elliptical distribution of circulation. So let's consider a general elliptical distribution of circulation, gamma of y, which is equal to gamma naught, okay, gamma naught into 1 minus 2y by b the whole square. Okay, this is a general distribution of circulation. It is an elliptical circulation distribution. So it is known as EDC. Okay, elliptical distribution of circulation. All right. Now, when you are given such a circulation, you can find out the downwash. So how will you find the downwash, guys? There's a formula to find the downwash, right? Which is minus 1 by 4 pi. You integrate it from minus b by 2 to b by 2, which is the span of the wings, right? D gamma by dy times dy by y naught minus y. Okay, so you have to basically evaluate this integral to find out the downwash. Okay, so if you just, it's very simple to integrate this. Okay, so you can assume y is equal to b by 2 cos theta. Okay, when you assume this, your dy becomes minus b by 2 sin theta d theta, and when you impose this condition, your limits will be changed from pi to 0. Okay, so you can use this transformation and do this integration. I am not doing it here, I'm leaving it for you to do. Okay, you can even refer John D. Anderson. It is a solved example in that elliptical distribution. When you do this integration, remember, when you do this integration, you will have to make use of a special integral called as Glover's integral. Okay, you have to make use of Glover's integral. Okay, so Glover's integral is a special, it's a very special integral which helps us to reduce the complex integral, definite integral forms. Okay, it will help you to solve this integral quickly. So you have to make use of this and then integrate this. When you integrate, you will get the downwash as minus gamma naught by 2b. So what do you find here? You find that the downwash is actually constant. The downwash is a constant. Okay, so for elliptical distribution of circulation, the downwash along the wingspan is constant. So guys, you tell me, if your downwash is constant and your V infinity is constant, what will happen to your induced angle of attack? Alpha I will also be constant. So from the options itself, you can see option C and D are not correct, right? Because they are not constants. So now we are left with A and B, right? So we have to decide between the sign. Okay, so let's now see that. Okay, so if you compare this with the question that is given to you, you will find that your gamma naught and B are what? Your B is 4, okay, and your gamma naught is 100. Okay, so you can find your alpha I. Alpha I is minus downwash by V infinity, which is nothing but basically gamma naught by 2B V infinity, which is 100 by 2 into 4 into V infinity is given to you as 100, right? So it is 100, which is 1 by 8, which is nothing but 0.125 radians. Okay, so actually in this question you don't even need to solve, right? You just have to understand that it is an elliptical distribution, and for an elliptical distribution, the circulation, the induced angle of attack is going to be constant. So you can just strike off option C and D. You have to decide between A and B, that too just the sign, right? How will you decide the sign? You know, induced angle of attack is negative, but downwash itself is negative, so it will become positive, right? So option A is the correct answer. Okay. So guys, a lot of questions in GATE actually do not require you to solve rigorous steps. You can actually guess the answer from the options by this elimination procedure. Okay. So make use of it when you are short of time. Okay. But it doesn't work always. You should not risk your luck over here. Okay. So let's move on to the next question. Okay. The next question is based on potential flows over lifting cylinder. Okay. So they have given you potential flow over a spinning cylinder. You have a cylinder which spins. You have given it a rotation. Stream function is given to you. Okay. The free stream velocity is given. The radius of the cylinder is given. And the circulation is also given. Okay. Let's see what is the question. The question is about radial and azimuthal velocities on the cylinder. So it is fairly simple, right? So when you have a cylinder, okay, you have a cylinder which is spinning, you give it a circulation, which is gamma. You can write the stream function, right? So what is the stream function here? Stream function is, they have given you the stream function, right? So take this down, V infinity R sine theta into 1 minus R square by R square plus gamma by 2 pi ln R by R, right? Okay, it is ln R by R. Okay, this is the stream function that is given to you. So how will you obtain the velocity components from the stream function, guys? You will have to differentiate it, right? So that is how the stream function is defined, right? It is defined from the incompressibility condition. So what are the velocity components here? Vr and v theta. Now, without even calculating these velocity components, you can readily see that when you have a flow over a cylinder, there is no radial component of velocity at all, right? Because the flow is going to be tangential to the surface of the cylinder, right? The flow is going to be attached because it is an inviscid flow. It is an inviscid flow. It is a potential flow. So it's going to be attached. There is no slip condition. No slip condition is not necessarily satisfied here, right? So the flow will slip. So the only component of velocity is v theta. Vr will be equal to 0, right? You can obviously, of course, differentiate and find out Vr, but you don't need to find out, right? Because we are finding it on the surface. On the surface of the cylinder, there is no radial component. You will only have the azimuthal component. Now, how will you find azimuthal component? It is minus dou psi by dou r. Okay, so just differentiate it. What will you get? Minus v infinity sine theta into 1 minus or 1 plus r square by r square minus gamma by 2 pi. Okay, differentiation of ln is, right, 1 by r into 1 by r, right? So this gets cancelled out, and you want to find it at the surface of the cylinder, right? So at the surface of the cylinder, your r is going to be the radius, which is capital R. Okay, the radius of the cylinder is capital R. Okay, so your v theta is going to be minus 2 times v infinity sine theta minus gamma by 2 pi r. Okay, and you want to find the azimuthal velocity at theta equal to pi by 2. So all the values are given to you. You just have to substitute. If you substitute, what will you get? Let's substitute this. So v theta is equal to minus 2 times, what is v infinity given to you? V infinity is 25 meters per second minus gamma is 50 pi by 2 pi r. Okay, R is, I think, R 1 meter, right? R is 1 meter. So this becomes minus 75 meters per second. Okay, so you see that option A is the correct answer. VR is 0 and V theta is minus 75. Okay, all right. Let's now move on to the next question. Next question is a similar one. So it was a linked question. You have a common question and there are two subparts, right? So we have finished the first subpart. The second subpart is the stagnation points are located at which location. So you know when you have the flow over a cylinder, a lifting cylinder, the streamlines somewhat look like this, right? So you know the stagnation points lie somewhere in the third and the fourth quadrants, right? For a positive value of circulation. Okay. But we can still find it out, right? So we have derived an expression for V theta, right? The azimuthal velocity. You take this and equate it to 0. Okay. So you know V theta is minus 2 V infinity sine theta minus gamma by 2 pi r. Okay, you equate it to 0 because we know VR is already 0, right? There is no radial component of velocity. So you equate V theta to 0. When you equate it to 0, what will you get? Sine theta is equal to minus gamma by 4 pi r V infinity. From here you get theta is equal to sine inverse minus gamma by 4 pi r V infinity. Okay, you substitute the values, what will you get? Theta is equal to sine inverse gamma is 50 pi by 4 pi, r is 1 and V infinity was 25, right? Okay, so this is pi cancels, this is 2, so 2, there's a minus sign here. So what you get? Theta is equal to sine inverse minus 1 by 2, right? You get theta is equal to sine inverse minus 1 by 2. So what is sine inverse minus 1 by 2, guys? Right, so if you see the circle, okay, sine 1 by 2 is 30 degrees, right? But it is negative, you know, sine is going to be negative on the negative y-axis. So it is like 30 degrees from here, okay, 30 degrees from here. So both these points, now these points are in the sense, so you have to subtract 2 pi, right? 2 pi minus pi by 6. Okay, so what do you get? You will get 210 degrees, or this is one solution, or you will also get 330 degrees, right? So these are the two stagnation points and they are located at the third and the fourth quadrants. Okay, so you see option A is the correct answer. Okay, so in this case, because your gamma is less than 4 pi r V infinity, your stagnation points are going to be on the surface of the cylinder and you will have two stagnation points. Say if your gamma was exactly equal to the denominator, you will have only one stagnation point and that will shift to the bottommost point of the cylinder. If your gamma exceeds the denominator, then your stagnation point will lift off the surface of the cylinder. Okay, it will be somewhere else, right? So this is about the flow over lifting cylinder. Okay, so again this you can refer from J.D. Anderson. So there is a chapter on complete elementary flows and their superimposition. Okay, definitely one question can be expected from that part in GATE. Okay, all right, so I hope this is clear to you all. So that's all, I think we are done. Thank you. I hope this session was useful for you guys. If there is any doubt, please feel free to ask. Okay, then we can wind up the session. I think we have next session lined up.